Is it recording now? Does it say recording, guys?
Yeah, it's recording.
Thank you. All right. Any questions? I got your homework. I graded them. Some of you got a couple problem wrong. I did not penalize you. There are two people submitting individual homework. That's okay, but as long as you know you're supposed to form a group. But if you prefer to submit individual homework, that's fine too. Okay. I mean, I'm not gonna be picky about it.
Can you also turn on AI summary, please?
Huh?
Can you also turn on AI summary.
I thought I did. Okay. Is it now?
Yeah, it is.
All right. Thank you. Does it help? How do you see AI summary? Do you see it along with the video?
Yeah, it helps because we can take a quick look of the whatever we're covering in the class without going
Okay.
through the whole video.
All right. Do you get an email about it or not?
Yeah, we get an email.
Oh, okay. Oh, good. All right. The videos, it seems like UD site is really giving me a hard time. So I think I have better luck with my channel on YouTube. And you can access that channel from syllabus page. Click on the link, it will take you to my YouTube. Okay. And they are labeled video 1, 2, 3, and so forth. So I'm not going to bother with UD website anymore. I don't know. The other two did not upload. And it's taking so much time. All right. Now we're going to take a look at, now we are in section 2.2. Okay. So we're going to look at the non-homogeneous difference equation xn plus 1 equal to an xn plus gn xn. And remember, this is for n bigger than n0 and n belong to z plus. Okay? So that means, so it's like 1, 2, 3, and so forth. Anyway, so this is non-homogeneous. Well, I mean, it could be non-homogeneous, and this is non-linear. And this is the non-linear due to the nature of G. Okay? Due to the nature of G, so this is a non-linear. All right? So, in other words, we're going to look at xn plus 1 equal an xn plus gn xn. Okay? And this is I labeled 2.2.1. That is the label. Is the ink dark enough, or should I change the pen, the marker? All right. Remember from last time, we looked at, okay, I'm gonna change the markers. All right. Okay, if we have S equal A to B, X of S that equals 0 if A is bigger than B, and the product S equal A to B, X as that equal to 1 if A is bigger than B. Remember, this is stuff we did last time. I mean, we defined. This is we're gonna agree on. Okay? All right. Recall the integrating factor of x prime of t equal at xt plus some function at gt xt. This is a continuous case. Is mu equal e to the minus t0 to t as dx, e to the minus. So that is called the integrating factor. Okay. Why is that? This is true because d of dt of mu x of t, look at that, is equal to mu x prime of t plus mu prime x of t. Okay, well, let's check. Okay, let us check. So what is d of dt of e to the minus t0 to t as x of s ds x of t? That is the derivative of that. So that is minus, okay? All right, so this is equal to minus a t e to the minus t0 to t as, sorry, no, there's no xs here. This is ds, x of t. It's minus at e to the minus as ds x of t plus e to the minus t naught to t as ds x of t. Okay. All right. So, and you will see why this is. So anyway, and you will see this is mu. This is a mu x prime plus a mu prime. This is a mu prime x of t. All right. So today we're gonna take a look at the discrete case. Okay. So the integrating, instead of integrating, we're gonna call it, I wrote it intentionally, the product, I call it the product factor, a mu of 2.2.1 is, okay, is a mu of n equal to pi s equal n 0 to n a inverse of s, provided that an is never equal to 0, or all n belong to z plus. And here, a inverse of s is 1 over as, okay? So you know what the definition is. All right. Any questions? Okay, now I'm gonna erase this and I'm gonna write, this is theorem 2.2.1. Suppose an is never 0 for all n belong to n. This means, okay, so sometimes we can go from minus infinity to infinity. So let's keep it to n natural numbers or positive. All right. Okay, so for all n in n naught, and remember what n naught is. It's n naught plus 1, n naught plus 2. This one. This is n of n naught. That means you start with the n naught. And n naught is the initial point. All right. Then xn is a solution of 2.21. Okay, if and only if and only if xn equal to x naught, s equal n naught to n minus 1 as a plus sum r equal n0 to n minus 1, a product s equal r plus 1 to n minus 1 as, and it's gonna be g of r x of r, and that is 2.6. So this is the solution. This is called the variation of parameters formula. So equation 2.2.6 is referred to as the variation of parameters formula. Variation of parameters, okay? It's a solution. So that is a solution to that one. Okay? So the way I'm gonna start, okay? So proof. So we're gonna go this way. Assume xn is a solution of 2.21. So we're gonna assume it solves 2.21. We don't know what it looks like. And we need to verify, we need to show that xn is given by 2.26. Okay? Any questions? All right. So we're gonna multiply both sides of 2.21 by the integrating factor may I say the product factor, sorry. The product factor mu equal to pi s equal n0 to n a inverse of s. Okay, let's make S to be capital. I don't care if I write S as a capital, I mean the same S, okay? All right. So that is, so we're gonna multiply this. So we're gonna have xn plus 1 s equal n naught to n a inverse of s equal to an s equal n naught to n xn. Okay. Oh no, sorry. This is an times pi s equal n naught to n a inverse of s xn plus jn xn by s equal n naught to n a inverse s. Okay. All right. So, or I'm going to reduce this a little bit. So I'm going to have xn plus 1 s equal n naught to n a inverse of s minus, I'm going to bring this one over here, an pi s equal n naught. Okay. Sorry. I'm not gonna, I wanna save myself some room. I'm gonna simplify this a little bit right away. I will explain to you. Equal to gn xn s equal n naught to n a inverse of s. Now, what happened here? You see what happened? The an disappeared, and then the upper limit for the product became n minus 1 instead of n. Why is that? Well, let's take a look. An, the product s equal n naught to n a inverse of s. That is what? So this is an times a inverse of n times the product s equal n naught to n minus 1. Do you agree with that? I evaluated the product at n. And this is 1, isn't it? An times a inverse. And so you are left with this. Okay? Everybody okay with that? Can you see the picture good, or should I get a bit closer?
Yeah, it's good.
All right. So this is why I was able to write this. Now, I'm sure this I labeled in my book. It's 2.27. So that equation is 2.2.7. Okay? I'm going to flip the board and you see if you have any questions. Okay. All right, so the left hand side of 2.2.7 is equivalent to del of xn s equal n naught to n minus 1 a inverse of s. You see that? Because since this one is equal to xn plus 1 s equal n naught to n a inverse of s minus xn s equal n naught to n minus 1 a inverse of s. Take a look at this. Isn't that this one? That is this one, isn't it? You see that? Okay. So I'm gonna get rid of this. Hence, we rewrite 2.27 as del of xn, the product s equal n naught to n minus 1, a inverse of s as equal to, over there, gn xn, the product of s equal n naught to n, a inverse of s. Well, that is the right hand side. You see it? Gn xn. That is, I'm not doing anything with the right hand side. Oops. Do that all the time, but that. Any questions so far? And this one, 2.28. Okay? Okay, so now we're gonna sum both sides of 2.28 from r equal n0 to r equal to n minus 1. So if I do that, that is r equal n naught to n minus 1. Now I'm going to have to change n here to r s equal n0 to r minus 1, a inverse of s, and that is, I have the del, you see, and that is equal to r equal n0 to n minus 1 g of r x of r, and this product becomes s equal n0, and the n turn into r, a inverse of s. Okay? Any questions so far? Okay. Well, now by theorem, we proved a theorem 1.4.2. We have, okay? Are you all okay with this now? Can I erase from here to here? from here to here. I'm gonna erase it. Give you a few seconds to look at it. All right. Don't answer it. Okay, I'm back. So this is XOR S equal N naught to R minus 1. And this is from R equal N naught to N. This is S. And this is, okay, now I'm gonna change the S to the majuscule so you know it from the R. Okay? And we're gonna go from R equal N0 to N, and that is equal to, there's nothing I can do with this. R equal N naught to N minus 1 G of R X of R S equal N naught to R A inverse of S. Well, replace R with N. So you get Xn, the product of S equal N naught to N minus 1 A inverse of S minus X of N naught S equal N naught to N naught to N minus 1 A inverse of S. Okay? So are you up to that one? Oh, this one is N naught minus 1. Sorry. Okay? Because I am doing from R equal N to N naught. When I put N in, I got Xn S equal N naught product N minus 1 A inverse S minus Xn naught product S equal N naught to N naught minus 1 A inverse of S, and the other one stays the same. The product of S equal N naught to R A inverse of S. Now, can anybody tell me what this is? What is that?
1.
1. Do you remember our convention? This is 1. So what I have is Xn, a product S equal N naught to N minus 1 A inverse of S equal to Xn naught plus R equal N naught to N minus 1 GR XR, the product S equal N naught to R A inverse of S. You see what happened? Okay. All right, now we're gonna multiply both sides with S equal n naught to n minus 1 AS. Think about it for a second. Why am I doing this? Okay, if I do that, this becomes 1 xn equal to x naught, because remember, xn naught is x naught, times the product s equal n naught to n minus 1 AS. Okay? A plus R equal n naught to n minus 1 g of r x of r, and I'm gonna have s equal n naught to n minus 1 AS times the product s equal n naught to r A inverse of S. Okay? Because I can bring this one inside, because the summation is done over R, and this term has no R. So I brought it inside. Okay? Now let us see how this is equal to, this is x naught, the product S equal n naught to n minus 1 AS, a plus R equal n naught to n minus 1 GR XR times the product S equal n naught to n minus 1 AS over the product S equal n naught to R AS. Okay? Now, what is that? Let's take a look at this one. What do you think? Okay, first of all, you need to know that R is smaller than n minus 1, because we are summing R from n0 to n minus 1. That means R is between n0 and n minus 1. So let me see what that is. Okay? So the product of S equal n naught, S equal n naught to n minus 1 AS over the product S equal n naught to R AS. Okay, so what is that equal to? So that is equal to A naught, AN naught plus 1, AN naught so we're gonna go all the way to AR minus 1 AR plus 1 all the way to AN minus 1 divided by AN naught plus 1 AR minus 1 AR. You see it? So all this, since it's a product, this cancels out, and you are left with AR plus 1 all the way to AN minus 1. And so this is the product of S equal to R plus 1 to N minus 1 AS. You see it? And look at it. Isn't that this one? Look at it. Okay? So we're done. But we only did it one way. All right? Any questions? And so this one equal to X naught, S equal N naught to N minus 1, AS plus R equal N naught to N minus 1, GR XR, a product S equal R plus 1 to A minus 1, AS. Okay? And that is exactly what we needed to show. Any questions? Now suppose the other way. All right. I'll leave it up to you for a few seconds. Any questions? Okay. We flip the board. So we proved this one. Okay. Now, the other way around of the proof. Suppose Xn is given by 2.2.6. Now, we need to show that Xn satisfies 2.2.1. Okay? So let Xn be given by 2.26. Then what is Xn plus 1? Then Xn plus 1 is, let's work with this one. X naught product S equal N naught to N AS plus R equal N naught to N, a product S equal R plus 1 to N minus 1 AS, and a G of R XR. Okay? Look, here I have N minus 1. So I'm gonna play with this a little bit to show that the solution is really indeed what we have. Okay, any questions so far? All right, so what is this? This is, if I evaluate, so this is AN X naught of S equal N naught to N minus 1 AS, okay? A plus, let's evaluate this at n. Let's evaluate R at n. A plus. If I evaluate R at n, I'm gonna have S equal to R plus 1. We're gonna evaluate R at n. So this is n plus 1 to n minus 1 as g of n xn, correct? This is only at n, plus the rest. R equal n0 to n minus 1, a product S equal R plus 1 to n minus 1 as, and then times g of R x of R. This is what I have. So what did I do again? I evaluated x. I said assume xn is given by this. Then I wanted to show it satisfied this. So the first thing I did is evaluate xn at xn plus 1. That means everywhere I saw n, I replaced it by n plus 1. So this becomes xn plus 1, n plus 1 minus 1 becomes n, and n plus 1 minus 1 becomes n. Now, you see my solution, I evaluated the product and the sum at the highest point, n. So for this to do it at n, I'm gonna have x naught, s at n, mean an x naught, and then I pick up and I keep the rest up to n minus 1. The same thing here, I evaluate R at n. That means if I evaluate R at n, this becomes s equal n plus 1 to n minus 1, because there's no R here, as, and then if I replace R by n, I get gnx, and then I pick up from the other one, I leave the other one, R equal n0 to n minus 1. Okay. Any questions? All right, so this is what I have now, and I evaluated R at n plus 1. All right, so this is what I have. Any questions? Let me see. I'm trying to figure out what I did here. Oh. When I did, you see, nobody helped me out. When I replaced n by n plus 1, this should have been n. I knew I had a mistake somewhere. Okay? This should have been n. Okay? All right. So what happened here is, if I evaluate R at n, so this is gonna be at n, as g and xn, and then this one, because I'm only doing R, that's gonna be n. Okay? S equal R plus 1 to n, and then this is the rest. Okay, I am gonna continue here with it. So I have xn plus 1 equal to an x naught, the product s equal n naught to n minus 1 as a plus. This is 1, correct? That is 1 plus an gn xn. Sorry, no. This is gnxn a plus. You see here, I'm gonna evaluate this at n. I'm gonna have an r equal n0 to n minus 1, the product s equal r plus 1 to n minus 1 as g of rxr. Okay, so now this is an x naught, the product of s equal n naught to n minus 1 as a plus r equal n0 to n minus 1, the product n minus 1 to s equal r plus 1 as g of r x of r, a plus this one. Okay, now what do you notice this is? What do you notice? What is this? What is that? Isn't that xn? Take a look at it. Isn't that xn? So that is an xn a plus this one. And that's it. That's the proof. Okay? Any questions? A little bit tricky, but it's really simple. It's not that hard to do. And I really went through all the details because a lot of the research in difference equation is based on this, being able to do this kind of manipulation. All right. Now, in the continuous case, that is if I have x prime of t equal atx of t plus gt x of t with xt naught equal x naught and t bigger or equal to t naught, then 2.26 takes the form x of t equal to, let me copy it down because I don't want to spend time on it. X naught exponential t naught to t a s ds a plus t0 to t g s x of s e to the s to t a. Okay, let's do this r g s to t as may I say, let's see, if I have this, I replace it by, u du plus t naught to t g of s x of s e to the s to t au du ds. All right, you see the product is exponential. The product here is exponential. Okay? So this is what really happened in the continuous case. All right. Any questions? All right. Okay, so we have several cases. One case I want to go over. Case A, n equal constant. Suppose that xn plus 1 equal axn plus g of r xr has the solution xn equal to x naught, and that is gonna be a to power n minus n naught plus r equal n0 to n minus 1 a n minus r minus 1 g of r x of r. That's what the solution look like. So basically, this one becomes this one. And this here becomes this one here. You see? Okay? All right. So let's do an example. Solve xn plus 1. By the way, this is 2.2.9. Okay? Xn plus 1 equal to 3 xn plus 5 to power n with x of 1 equal to 2. Okay? Any questions? So basically, so here, an equal to 3 equal constant, n naught equal 1, and x naught equal 2. So we're gonna use formula 2.2.9. Why don't you go ahead, work on it for a minute, then I'll pick it up for you. Go ahead. Try to use this formula, see what you can get with it. So you need to understand that the G here, the G is 5 to power n. Okay? It's raised to power n. There's no x in it. I just wanted you to do the setup. So let's do it here. Keep the theorem here. Okay, so xn equal to xn equal to x naught. We said x naught is 2 times a to power n minus n naught. A is 3 to power n minus 1. Okay, plus r equal 1 to n minus 1, a n minus r minus 1, 3 times n minus r minus 1 times 5 to power r. GRXR, that is 5 to power r. All right. So this is 2 times 3 to power n minus 1 plus 3 to power n minus 1. I'm going to take this out. R equal 1 to n minus 1 will be 3 minus r 5 to power r. So that is 2 times 3 to power n minus 1 plus 3 to power n minus 1 r equal 1 to n minus 1, 5 over 3 to power r. Now, do you remember the formula? Do you remember the formula? Q to power n or q to power r? I don't know what you call it. Is a qr over a q minus 1, remember? So this is 2 times 3 to power n minus 1 plus 3 to power n minus 1 of 5/3 to power r over 5/3 minus 1 from r equal 1 to n. Okay? See what we did? Now, so this is 2 times 3 to power n minus 1 plus 3 to power n minus 1. 5/3 minus 1 is 5 minus 3 will be 2/3 times 3.5 of 5/3 to power n from r equal 1, r to n. So this is 2 times 3 to power n minus 1 will be times 3n over 2. Okay? Plus. Because 3 to power n of 5/3 to power n minus 5/3. there. Okay? So that is your answer. Any questions? So we are done with this section, and I'm gonna move to a higher order. Any questions? Let's take a 5 minutes break and come back. I'm not gonna turn off the video. The video will stay the same. Let's take 5 minutes break. All right. Any questions? Okay. Now we're going to talk about higher order. This is section 2.3. As you notice, all we are doing is learning the calculus of difference equation, like you learned the calculus of Calc 1 and Calc 2. So this is what we are doing. We're learning the calculus of the discrete systems. That's what we've been doing. All right, now we're gonna take a look about how to find solution of higher order differential equation, difference equations. So higher order difference equation. Okay, so we're gonna assume n belong to n naught, and we're gonna look at the kth order difference equation ak xn plus k plus ak minus 1 xn plus k minus 1 plus ak minus 2 x of n plus k minus 2 plus a1 xn plus 1 plus a0 xn equal to fn. And we're gonna call this as 2.3.1. So here, the coefficient ai equal 0 all the way to k may depend on n. Okay, maybe variables. Okay. Now, if fn is equal to 0 for all n, then 2.3.9 to 1 is said to be homogeneous. Again, we are assuming here ak is not 0. If ak is not 0, then we do not have a kth order difference equation. Okay? All right? All right. So that is the homogeneous okay? The homogeneous equation associated with 2.3.1 is ak xn plus k plus ak minus 1 xn plus k minus 1 plus ak minus 2 xn plus k minus 2 plus a1 xn plus 1 plus a0 xn equals 0. And that is going to be 2.3.2. So that is a homogeneous equation associated with 2.31. Okay? Any questions? All right, definition. Let F1, F2, Fn be a set of functions defined on n0. Okay, then we say the set F1, F2, Fn is linearly dependent on n0 if there are constant C1, C2, all the way to Cn, not all zero, so that C1 F1 plus C2 F2 plus Cn Fn equals 0. Then we say they are linear independent. Okay? Take a look at the definition carefully. And see what we are doing here. All right. Now, if the set F1, Fn is not linearly dependent, then the set is said to be linearly independent. Okay? That is C1 F1 plus C2 F2 plus Cn Fn equals 0 implies C1 equals C2 equals Cn equals 0. This is what it means. Okay? If this is the case, then the functions are said to be linearly independent. Okay? All right. Definition, and this is 2.3.2, fundamental set of solution. Fundamental set of solution. A set of K solutions of 2.32 is called a fundamental set of solution on n naught if the set is linearly independent. Okay? In other words, each fi I equal to 1 all the way to n solves 2.32, and f1 all the way to fn is linearly independent. Okay? All right? Zero. Or I have a corollary 1. If phi1 of n, phi2 of n, phi k of n, okay, form a fundamental set of solution of 2.32, then the general solution of 2.32 is xn equals c1 phi n plus c2 phi 2 of n plus ck phi k of n. Okay? So these are the general solution. All right? Any questions? And the Ci are constant. So here, the Ci, I equal 1, 2, all the way to k are constant. Okay? Here's an example. Show that phi 1 equal 1, phi 2 equal to minus 2 to the n, form a fundamental set of solution for xn plus 2 for the second order equation xn plus 2 plus xn plus 1 minus 2xn equals 0, and find the general solution. Okay? So, first of all, we need to show phi 1, phi 2, each is a solution to, they are linearly independent. That's what we need to do. And then we can write down the the general solution or fundamental solution. Okay? Well, so that is what is phi 1 of n plus 2 plus phi 1 of n plus 1 minus 2 phi 1 of n. That is, well, phi 1 of n is 1. So that is 1 plus 1 minus 2, that is 0. There we go. That is good, right? Okay. What about minus 2 to the n? Phi 2 of n plus 2 plus phi 2 of n plus 1 minus 2 phi 2 of n equal to minus 2 n plus 2 plus minus 2 n plus 1 minus 2 times minus 2 to the n. Okay? So let's factor minus 2 to power n. So that will be minus 2 to power 2 plus minus 2 to power 1 and minus 2. Okay? So that is 4 minus 2 minus 2 minus 2 to power n, and that is 0 times minus 2 to the n, and that is 0. So we did this one. You see what we did? Okay, so we did the first one. All right, now for 2, C1 phi 1 plus C2 phi 2 equals C1 plus C2 minus 2 to power n, and that is equal 0 for all n. This is if and only if C1 equals C2 equals 0. So they are linearly independent. Okay? So they are linearly independent. Any questions? Now, what is the general solution? The general solution is xn equals C1 phi 1 of n plus C2 phi 2 of n. That is C1 plus C2 minus 2 to power n. Okay? All right, any questions? To completely describe the solution of 2.3.1 or 2.3.2, we need to impose the initial conditions at n naught plus 1 all the way to n naught plus k minus 1 as x n naught equal d naught, x n naught plus 1 equal d1, and x of n naught plus k minus 1 equal x of k minus 1, or a d, sorry, d of k minus 1. Okay? Where, so here, n naught is the initial point, and di from I equal 1 all the way to k minus 1 are constant. These are given. They are given constant. Okay? So for example, so here, for example, in this example here, k is 2. And let's take n0 equal to 1. Let's take. So let's and let's assume x of 1. So we're gonna start at 1. X of 1 equal to 2, and x of 2 equal 4. So we need to find C1 and C2. So let's use this one. So we have 2 equal x of 1, that is C1 plus C2 minus 2 times 1 to power 1, and 4 equal x of 2 equals C1 plus C2 minus 2 to power, okay? To power 2, all right? And so we have C1 minus 2C2 equal 2, and C1 plus 4C2 equal 4. Let's go minus plus minus, then I'll have 6C2 equal 2. C2 is 2 over 6 is 1/3. And then I have C1 minus 2C2 equal to 2. And so C1 minus 2 times 1/3 equal to 2. And C1 is 2 plus 2/3, and that is 8/3. Okay, there you go. So I found what the solution looked like. And so the solution, xn is C1, and C1 is 8/3 plus C2 plus 1/3 minus 2 to power n, and n bigger or equal to 1. Because we started at n naught. Okay? So if you like, so this is what we have. Any questions? All right. Definition. This is the Casso-Wrightian given two sequences F and G, the Casso-Wrightian of F and G is the determinant W equal to Fn